what we really care about is this concept of hexadecimal. And we need to be able to convert between denary or decimal to hexadecimal and the other way around. So first of all, let's talk about a concept that we've learned about our relationship. So we're saying we've learned about something called base 2. We've also learned about something called base 10. If you remember, with base 2, that was binary. And then you did the columns. You said lots of 1s and 2s, 4, 8s, etc. When we said it was denary, so that's base 10, it was 1, 10, 100, 1000, etc. This hexadecimal, it is base 16. And now we'll start with 1. What do you think the next column is going to be? Well, if you guess 16, you were right, because that's what it's multiplied. The next one you might think is 32, but actually it's times by 16. So 16 times by 16 will be 256. And then it will go onwards. But realistically, at the level we're talking, we only really care about these two columns here. Now, what we need to do is we need to have a go at converting, first of all, from hexadecimal into denary. Now, each of these in hexadecimal, each value can go up to 15. So in denary, if you looked at it, in fact, let's go back to the beginning. In binary, the biggest number you can have is 1. So it's 0 or 1. It's base 2. So you take 1 off that, gets you the value. The biggest value in base 10 is 9. Now you might think it's 10, but that's not true. A 10 is 1 lot of 10 and 0 lots of 1. In one column, the biggest you can have is 9. So 1 take off this. In hexadecimal, the biggest value you can actually hold in each of these columns would be 15, 1 off this. So I could write a hexadecimal number here, and I could say, well, let's pick a number. We'll say 1410. Okay, and you're like, well, how do I represent that? Well, that's straightforward. First column is 1s, second column is 16s, and you would say 14 times by 16 plus 10 times by 1. Oops. And hopefully you can see why that's the case, because here we've got 14 and 16s, and we've got 10 1s. So, for example, if I did it with denary, just to prove something, 27 in denary would be lots of 1s and lots of 10s. We could say it would be 2 lots of 10 plus 7 lots of 1. And so 20 plus 7, 27. Here, 14 16s, it's a bit trickier to do, isn't it? But it would be, what, 224, I think. 10 16s, 160, 4 16, 64, 160 plus, I think so anyway, plus 10 is equal to 234. Okay, brilliant, done. Now, I've actually cheated here a little bit, because here's the deal. Let's say I wrote out this number in denary, 79. Now, we can see straight away that's 1 lot of 9s and 10 lots of 7s. What if I give you this number in hexadecimal, 111? Okay, what does that mean? Do I mean 1 lot of 1s, 1 lots of 16s, and 1 lots of 256? Do I mean something different? I could mean 11 lots of 1s, right? And then 1 lot of 16. Could mean something completely different again. Could mean 11 lots of 16s and 1 lot of 1. Which one do I mean? I honestly don't know. And so there's a confusion. As long as you go over 2 characters long, you have a big problem. You have a big problem. To fix this problem, hexadecimal has a solution. So let's show you the solution. We'll do denary and we'll do hexadecimal. And then we'll run some numbers. So we start at 0, 1, 2, 3. Let's go up to 9. And then it's 10, 11, 12, 13, 14, 15, because that's the biggest number we can get. Then let's show the same numbers here in hexadecimal to just to the right of it. So we go 0, 1, 2, 3, 9, same deal. But we get to 10, just because that could be confusing. It could be 1 lot of 16, 0 lots of 1, hard to tell. We need to keep it to a single character. So what we do is we go A when we get to 10. And then what comes after A? B. So B is 11. What comes after B is C, D, E, and F. So essentially, what we're talking about is that the implication is that if we see the letter D, don't be thrown off by it. What it means is actually it's the number 13. If we see the letter E, it's actually the number 14, and so on. Okay, now I think we've laid the groundwork, so let's start talking about how we could convert numbers. So let's see a couple of numbers in hexadecimal. So we've got one here. We're going to say 4D. Let's do exactly what we did with binary and denary to do before. The first column will be lots of ones. This is base 16, so the next column is 16s. And now we can do the calculation. So it's 4 times 16, okay, plus D times 1. That will give us our number. Now, the thing is, D is not a number. We know that. So we can come over here and see, it's 13. Now, you're not going to be given this in an exam. So what do you do if you can't remember what D is? Here's what you do. You can remember that A is going to be 10, because that's the first time you get to 2 digits. And then B would be 11, C would be 12, D gets you 13. So we come back over here, we get rid of that D, because that is not what it is. It's going to be the number 13. And so it's going to be 4 times 6, which is going to be 64 plus 13. So that's going to give you 77. Right, let's try it the other way around. The other way around is a bit trickier. By that I mean going from denary to hexadecimal, but let's pick a number. Let's say we want to turn 54 into hexadecimal. How do we do it? Well, first of all, we write out the columns, 1, 16, and we do exactly what we did with binary. By that I mean we go left to right, and we say, how many can 16 fit into 54? Now, it's different this time, because it's not just can 15 go into 54, it's how many times, and how many whole times. Well, 1 16 16, 2 16 32, 3 16 48, 4 16 64, that's too big, so it must be actually 3. So we can put 3 16s, and we do just the same as we did before, that we need to accommodate it. So 3 16s was 48, 54, take away 48, it's going to leave us with 6, and so that's what we left here. So what's 54 in hex? It's 3 6.